the purpose of this lecture was introducing very basic but very important concepts such as maximum likelihood, maximum a posteriori, and fully Bayesian analysis. And in order not to get distracted by examples that are too complicated, we looked at this very, very simple experiment, namely a sequence of coin flips. And admittedly, this is not the most interesting data set and not the most interesting experiment, but it helps a lot in understanding how to do these estimates. What I'd like to do towards the end of this video is to give you an application where you can see that these tools have widespread applications and can actually be very, very useful in real life. And this application is known as the German tank problem. What is the German tank problem? Well, during the Second World War, the Allied forces would like to have an estimate of the number of tanks that the Germans had. Because apparently if you know this number, then you have strategic advantages, because you know that if you observe that and that many tanks in one battlefield, you know that they can only have that many tanks in another battlefield, for example. So how do you get reliable information on that? Well, you can send spies to the War Ministry, or you can send spies to the factories that are producing the tanks. But these are, of course, all very dangerous missions, and chances that you get wrong information are quite high. So there were some intelligent statisticians that knew the exact concepts that we were using today. But they needed data. And they found a clever way of using data. They looked at tanks that had been bombed and destroyed and captured by the Allied forces. German tanks in the hands of the Allied forces. And these tanks, the parts of these tanks had serial numbers on them. And the Germans had made a big mistake. The mistake was that they had actually taken serial numbers literally. So that the first tank had the serial number 1, the second tank had the serial number 2, and so on and so forth. And now the statisticians observed the following. They observed that if I get, for example, 3 tanks, and they have the numbers 1, 4, and 10, it's very unlikely that the Germans have 1,000,000 tanks. Whereas if I got 3 tanks with the numbers 1, 50,000, and 814,000, then it's much more likely that the Germans have 1,000,000 tanks. And of course, the numbers were not that extreme, but they used Bayesian analysis on these serial numbers to estimate how many tanks the Germans have. And now let's look at the numbers. The statisticians estimated that the Germans have between 170 and 330 tanks. At the same time, the conventional intelligence, so spies that gather information, estimated that they must have 10 times as many tanks. After the war, when the Allies captured the German records from the factories, they found that the estimates of the statisticians were actually very, very accurate. But of course, during wartime, they trusted the intelligence estimates. But if they had trusted statisticians, they could have probably adapted their strategies and maybe ended the war earlier. And if you want to read more about this and how they did this and want to read a more elaborate analysis, I can refer you to the Wikipedia article, which is actually a quite nice article about this very nice and very interesting application of Bayesian analysis. The only thing that is left to do now is to summarize the key learnings of this video and these slides. And of course, there are the 3 big concepts we've been talking about all the time: maximum likelihood, maximum a posteriori, and fully Bayesian analysis, which naturally extend to each other. But this increasing capability, of course, comes with increasing computational complexity. So we would always like to do fully Bayesian analysis because it's the most correct way of doing it, but it's also the most complicated way. And if we have enough data, then maximum likelihood might actually be preferable, because the pain of the calculations is not worth the extra correctness, so to speak, if we have enough data. And while we were talking about these concepts, we also learned about prior, posterior, and likelihood, and we found that the posterior, which is the distribution of our parameter given data, is connected to prior and likelihood, and it's actually proportional to the product of the prior times the likelihood, and that's a consequence of Bayes' formula. And we also talked about the Iid assumption, which we will oftentimes implicitly do from now on. But it's important to remember that the Iid assumption actually allows us to extrapolate from previous data to unseen experiments. And then we also talked about the conjugate prior, which is a reasonable choice for the prior because it eases calculations, among a lot of other nice features that conjugate priors have. So these were the concepts that we were talking about in this lecture and that you should keep in mind. And then we also found some nice tricks. The first trick was that we found that when we were optimizing a function, sometimes taking the derivative is very complicated. But often we were only interested in the position of the maximum, not really the value of the maximum. And if that is the case, what we can do is we can do monotonic transforms, like taking the logarithm to turn products into a sum, which are much easier to differentiate. And the second trick was solving integrals by reverse engineering densities. So when you have an integral that looks complicated but also looks like the integral over a PDF up to a constant, you can easily reverse engineer the result of this PDF. And these are two very handy tricks you should keep in mind. Thank you for listening.